Goal of this video is to learn comparison test and limit comparison test to test the series convergence. So far we've talked about nth term divergence test, geometric series to test for convergence or divergence, integral test, and p-series test. So sometimes we have a series with the complicated terms. We're going to try to do comparison with a series that we know for sure converges or diverges. So our goal would be to compare it to a series with a simpler series whose convergence or divergence is known. The direct comparison test is a tool that we can use to determine convergence of complicated positive series by comparing them with simpler series. Direct comparison test. Let an and b 0 less than an less than equals bn for all n. So if bn converges, then an also converges. If an diverges, then bn also diverges. That means if the bigger one diverges, we cannot say anything about the smaller one. So here, if the bigger one converges, then we can say smaller converges. If bigger one converges, we can say smaller one converges. If smaller diverges, we can say bigger diverges. If smaller diverges, we can say the one that's bigger also diverges. But if bigger one diverges, we cannot say anything about the smaller one. The smaller one might diverge or converge. We cannot say anything about smaller series, anything about convergence or divergence of smaller series if the bigger one diverges. Okay, so keep that in mind. We cannot say anything about smaller one. Okay, so remember, both parts of the direct comparison test require the series to be greater than 0. Normally, the test says the following about two series with non-negative terms. Just like we said, if the larger series converges, the smaller series must also converge. If smaller one diverges, then the larger one must also diverge. Let's see some examples. So here we have 1 over 2 plus 3 to the power n. Our goal will be to compare it with either a p-series test or a geometric series test that we know for sure that does converge or diverge. So here we will compare it with this one. We can compare with summation n is equal to 1 to infinity 1 over 3 to the power n. So I can say 3 to the power n is less than 3 to the power n plus 2. And if I go ahead and do reciprocal of these, then the sign will flip. So that means summation n is equal to 1 to infinity 1 over 3n plus 2 is smaller than summation n is equal to 1 to infinity 1 over 3 to the power n. Do I know something about this series? N is equal to 1 to infinity 1 over 3 to the power n. I do know this is a geometric series. Each time I'm multiplying with 1/3. So this is a geometric series with r equals 1/3. So this series converges. So using direct comparison test, we can say the series we were talking about converges. So using direct comparison test, the series in question, n is equal to 1 to infinity 1 over 2 plus 3 to the power n, converges. Again, we're not looking for what does it converge to. We're only trying to decide if it converges or diverges. In some cases, it's not even possible to find out what does the series converge to. So this series does converge by using direct comparison test. Now we're going to look at the next one. So I'm going to erase the work for the first one so I have more room. For the second problem, we have summation 1 over square root of n minus 2. So what series should we compare it with? Let's compare with 1 over square root of n. So here our summation 1 over square root of n. So we're going to compare with 1 over square root of n. So here's something to keep in mind, that if whenever you're thinking about the series you want to compare with, one, that it has to be either geometric series or p-series that you know for sure about convergence or divergence. Second, you either want to find out a bigger series than yours that converges, or you want to find out a smaller series than your series that diverges. So that's what your goal. Either you're trying to look for a bigger series that converges, or you're trying to find a smaller series that diverges. So in this case, I'm going to go ahead and say square root of n is always greater than square root of n minus 2. And when we do the reciprocal here, the sign of fraction will flip. So summation n is equal to 1 to infinity 1 over square root of n is always going to be less than summation n is equal to 1 to infinity 1 over square root of n minus 2. Now, do we know something for sure about this series? We know this series 1 over square root of n is diverges. So summation n is equal to 1 to infinity 1 over square root of n diverges because it's a diverges by p series test. Because here your p is 1/2. If your p is between 0 and 1, the series diverges. So this series diverges. So using direct comparison test, we can say the series we were looking at, summation n is equal to 1 to infinity 1 over square root of n minus 2 diverges. So if the smaller series diverges, this one is going boundless, then the bigger one will also go boundless. If the bigger series diverges, then we cannot say anything about the smaller one. But if the bigger one converges, we can say the smaller one will also converge. Let's see another example. 1 over 4 cube root of n minus 1. Here again, we want to use direct comparison test. When we think about direct comparison with series to compare it with, we need to keep two things in mind. One, that it has to be a simpler series. It has to be either p series or geometric series that we know for sure that either converges or diverges. Second, we want to be able to show that the bigger series converges than the one we have, or smaller than that diverges. So that's our goal. If you are able to show that the series bigger than yours diverges, that doesn't tell us anything, so that wouldn't help. Let's see, for this one, we can try to compare with 1 over 4 n to the power 1/3. Now for this series, we know it's a divergent p series. This is a divergent p series. So let's compare 4 n to the power 1/3. 4 n to the power 1/3 is greater than 4 n to the power 1/3 minus 1. And if I go ahead and do the reciprocal, 4 n to the power 1/3 is less than 1 over 4 n to the power 1/3 minus 1. So my sign would switch. So I do have a smaller series that diverges. That means it's going boundless. So I can say summation n is equal to 1 to infinity 1 over 4 n to the third less than summation n is equal to 1 to infinity 1 over 4 n to the power 1 over 4 n to the power 1/3 minus 1. So we know this smaller series diverges. This one is divergent. We know that it's a p series. So if the smaller one diverges by using direct comparison test, we can say that the larger one also diverges. Direct comparison test, we can say summation n is equal to 1 to infinity 1 over 4 cube root of n minus 1. Let me write it slightly better. The n, 4 doesn't look. 4 cube root of n minus 1 diverges. So this is also a divergent series using direct comparison test. I'm going to talk about limit comparison test. Limit comparison test is usually easier to use than the direct comparison test. Sometimes direct comparison test makes it harder to prove which series is bigger, which series is smaller, so we would end up using the limit comparison test in this case. So some series closely resemble others, but you're unable to apply the direct comparison test. If that's the case, then there's a second comparison test called limit comparison test. For example, here, so where direct comparison will not work, but the limit comparison will work. Let's see, limit comparison test. Suppose an is greater than 0 and bn is greater than 0, then limit n goes to infinity an over bn is equal to L, if L is a finite positive number, then the two series either both converge or both diverge. So if L is finite and positive, then L cannot be equal 0 and it cannot equal infinity. So that means when we find the limit n goes to infinity, the series an over series bn, then I should be getting something non-zero, a finite number. If that happens, then either both of the series converge or both of the series diverge. So helpful examples in choosing appropriate p-series when using comparison tests. So if I'm trying to compare this series, I'm going to only care for the leading term. So I'm going to compare with this one. If I'm using 1 over square root of 3n minus 1, I'll be comparing with 1 over root n. So when I choose the limit comparison test, I'm choosing a series by myself and then finding the limit of the given series over the series I chose. If that limit is a finite number, it's non-zero, finite number, then either both series converge or both diverge. Here, again, I'm going to care for the leading terms. So n squared over n to the fifth would be 1 over n to the third. Let's see some examples of limit comparison tests. So here we have square root of n over n squared plus 1. What should we compare it with? So let's think about what to compare it with. So what series should we compare it with? Seems like I can think about the leading terms, square root of n over n squared, which is going to be 1 over n to the power 3 halves, 1 over n to the power 3 halves. So that's going to be my bn. My an is given, and that's going to be my bn. So I'm going to go ahead and find limit n goes to infinity an over bn. So limit n goes to infinity, an is square root of n over n squared plus 1 divided by bn. So I'm going to divide it with the series bn, which is 1 over n to the power 3 halves. Okay, so limit n goes to infinity. The series bn we chose, do we know anything about this series? Do we know if it's convergent or divergent? 3 halves is greater than 1. So this is a convergent p-series. We already know that. That's why we chose it, because we know the behavior of this series, definitely. So limit n goes to infinity, square root of n over n squared plus 1 times n to the power 3 halves. And that's going to be limit n goes to infinity. N to the power 3 halves plus 1 would be n to the power 5 halves over n squared plus 1. And 3 halves plus 1 half. Oh, I'm sorry, not 3 halves plus 1 half. Is 3 half plus half, which is going to be 3 half plus half is n squared. Now we know when n goes to infinity, this is actually infinity over infinity form, so I can use L'Hopital rule, or I can go ahead and use some other techniques to evaluate this limit. So limit n goes to infinity. If I use L'Hopital rule, this would be 2n over 2n, still infinity over infinity. Limit n goes to infinity, L'Hopital rule applies one more time. We can do the derivative of numerator over derivative of denominator. This limit turns out to be equal to 1. So if the limit is a non-zero finite number, then either both series converge or both diverge. So we got a non-zero finite number, and we know our bn converges. So we can say thus by limit comparison test, summation n is equal to 1 to infinity, square root of n over n squared plus 1 converges. That's all we were looking for. Again, we may not be able to find out what does it converge to. In some cases, we really cannot find out what does a series converge to, but we can tell the behavior of series if it converges or it diverges. Okay, next we have next example, n 2 to the power n. So let me make some room for the next problem. All right, for the next problem, we have part B, summation n 2 to the power n over 4n to the third plus 1. So what should we compare it with? Let's see. Let's compare with, we want to find out a simpler bn that we know the behavior of bn for sure. So bn would be, we can do n 2 to the power n over n to the third, n 2 to the power n over n to the third. We can compare it with that, which is going to be 2 to the power n over n squared, 2 to the power n over n squared. Now this series 2 to the power n over n squared. We did it in the beginning of this chapter. We use the nth term divergence test. So this series diverges. This is a divergent series using nth term divergence test. We saw that the 2 raised to the power n grows very, very fast as compared to n squared. Diverges using nth term divergence test. Nth term divergence test. So we know something about the series Bn. That's going to be my Bn. So let's go ahead and find the limit. Limit n goes to infinity an over Bn, which is limit n goes to infinity. An is n 2 to the power n, n 2 to the power n over, oh no, n 2 raised to the power n, get rid of this little dot, over 4n to the third plus 1 divided by or 2 to the power n over n squared. So turns out to be limit n goes to infinity n 2 to the power n over 4n to the third plus 1 times 1 over n squared goes in the denominator, n squared goes in the numerator, and 2 to the power n goes in the denominator. So that's going to be gone, and we're left with limit n goes to infinity n to the power third over 4n to the third. And we do know that this limit is going to go to 1/4. This limit is going to go to 1/4 when n goes to infinity. We can use a L'Hopital's rule, or we can divide both numerator and denominator with n to the third. We can also see that it's a rational function with the same degree of numerator and denominator. So there's multiple ways of finding the limit for this function. So 1/4 is going to be the limit. Again, it's a non-zero and non-infinite number, so either both series diverge or they both converge, and we do know about the Bn that that's divergent. So using limit comparison test, this series summation Bn, not summation Bn because that's what we brought in, we actually wanted to find behavior of n is equal to 1 to infinity n 2 to the power n over 4n to the third plus 1 diverges. Okay. Another example, 1 over k square minus 5k plus 1. So what should we compare this with? Again, we want to only care about the leading terms or leading coefficients. So I'm going to bring Bn, that would be 1 over k square. Bn would be summation. Let's choose Bn be summation k is equal to 1 to infinity 1 over k square. And we do know that this Bn, we know about the Bn, this is a convergent p series because my p is greater than 1. P value is 2 here, which is greater than 1. So let's do the limit comparison test. Limit k goes to infinity 1 over k square minus 5k plus 1 divided by 1 over k square. Limit k goes to infinity, k square over k square minus 5k plus 1. And again, we can use L'Hopital rule because this is infinity over infinity form, so we can say L'Hopital rule applies. L'Hopital rule says go ahead and do the derivative of numerator and derivative of denominator. Again, this is infinity over infinity form, so I can say L'Hopital rule applies one more time. L'Hopital rule applies one more time. So that's going to be limit k goes to infinity 2 over 2 again, which turns out to be 1, which is a non-zero finite number. So that means either both series converge or they both diverge, and I already know that the one we compared with, that was a convergent p series. So we can say by using limit comparison test, the series in question we had, actually k is equal to 1 to infinity. K is equal to 1 to infinity 1 over k square minus 5k plus 1 converges. This is a convergent series. Now it isn't a p series, but we could compare it to a p series and then go ahead and prove that this is convergent. Let's see part D. we have next. So again, I'm going to clear the, okay, clear the, let's look at next, part D. So here again, we are only concerned about looking at the leading term. So it seems like the Bn, I will compare it with, Bn would be, in this case, I can do square root of k to the third over 2k to the fourth, which if I simplify, that would be 1 over 2k. 1 over 2k, square root of 1 over 2k. Half. So Bn would be summation n is equal to 1 to infinity Bn, which is going to be summation n is equal to, oh no, it would be k in this case, because let's call it bk, or we can call it Bn, it doesn't really matter. K is equal to 1 to infinity 1 over square root of k, k to the power 1 half. So let's use the limit comparison test. Limit k goes to infinity, an over bn. Limit k goes to infinity, maybe I should call it ak and bk because the variable is k in this case. So ak, bk, I'll just call it k is here. bk, k is equal to 1 to infinity. All right, ak and bk, k goes to infinity. Now ak is square root of k to the third plus 1 over 2k to the fourth minus 1, and we're going to divide it with 1 over square root of 2 k to the power 1 half. Okay, all we need here is a little bit cleaning up. So this is like k to the power 3 halves, square root of 2k. So we have k to the power 2k to the fourth minus 1 times square root of 2 square root of k. And I would be able to take square root of k inside. When I take it inside the square root, it would actually become, I would be taking the k inside. Okay, so limit k goes to infinity. If I want to take it inside the square root, I would be taking a k inside. So k times k to the third plus 1 over square root of 2k to the fourth minus 1. Turns out to be limit k goes to infinity, k to the fourth plus k over 2k to the fourth minus 1. Now at this point, we can go ahead and divide both numerator and denominator with, we can divide both numerator, there was a square root of 2 as well. We could take the square root of 2 in here. Don't drop that square root of 2. We can just take the 2 in here, so that would give us 2k to the fourth plus 2k. 2k to the fourth plus 2k. Now this limit, we know it looks like it's got the same degree in the numerator and denominator. We can go ahead and divide both numerator and denominator with the k to the fourth power in a square root of k to the fourth, or we can just see from here that this limit is going to go to 1. If the limit is going to 1, then either both series converge or they both diverge. And we do know that the series we started with, that is a divergent p series, because the p is 1 half. P is less than, p is between 0 and 1. So Bn diverges using p series test. Thus, using limit comparison test, limit comparison test, the series we were looking at, summation k is equal to 1 to infinity square root of k to the third plus 1 over 2k to the fourth plus 1. This series also diverges. This series also diverges because we could find a series which is, we could compare it, we could use the limit comparison test, and our limit came out to be non-zero, non-infinite number. Okay, a couple more examples of limit comparison test. Again, when you're trying to think about your BE, you want to keep two things in mind. You either want to find a series, you either want to find out, or you want to find out a series. We're not doing direct comparison, we're doing limit comparison. You want to find out a series whose behavior you know for sure, and it's simpler than the series you're looking at. So here we have bn would be nth n to the 4 square root in the numerator and n to the 6 in the denominator. So we're going to only be concerned about the leading terms of numerator and denominator. And that would leave me with n square over n to the 6, which is going to be 1 over n to the 4th. So we would be comparing it. So my bn is summation n is equal to 1 to infinity 1 over n to the 4th. What do I know about this series? I know that this is a convergent P series. This is a convergent P series. So I already know that this series converges. Now let's go ahead and do the limit comparison test. Limit n goes to infinity. What happens if the limit turns out to be 0 or the limit turns out to be infinity? In that case, the limit comparison test would be inconclusive. We would not be able to say anything based on limit comparison test. So limit n goes to infinity, n to the 4th plus 1 over n to the 6th plus 2n minus 3 divide with 1 over n to the 4th. Limit n goes to infinity, n to the 4th plus 1 over n to the 6th plus 2n minus 3 times n to the 4th. Okay, limit n goes to infinity. So what can I do here is I can go ahead and take the n to the 4th inside. When I take this n to the 4th inside the radical, it would become n to the 8th. So I'm going to take it inside the radical and make it n to the 8th. So I'm going to be doing n to the 8th. Instead of when n to the 4th goes inside the radical, it becomes n to the 8th power n to the 4th plus 1 over n to the 6th plus 2n minus 3. Limit n goes to infinity, n to the power 12 plus n to the 8th over n to the 6th plus 2n minus 3. So this limit, because the numerator and denominator have the same exponent, they're the same degree. To really see how it happens, we can go ahead and divide both numerator and denominator with, we can divide both of them with square root of n to the 12. So really see the limit. We can divide both numerator and denominator with square root of n to the power 12. So 1 over square root of n to the power 12 over n to the power 12 n to the power 8 over 1 over n to the power 12 n to the power 6 plus 2n minus 3. Okay, that's going to leave me with square root of 1 plus 1 over n to the power 4 over 1 plus 2n over n to the power 6 minus 3 over n to the power 6. And we know the limit n goes to infinity. When n goes to infinity, all the terms where n is in the denominator, all these terms are going to go to 0. So this limit turns out to be equal to 1. If the limit is equal to 1, then either both series converge or diverge. We already know the bn converges, so we can say using direct comparison test, this series also converges. Always state what you're using to say that the series converges or diverges. So in this case, we would say using limit comparison test, the series converges. Another example of limit comparison test. Let's check this one out. Summation n equals 1 to infinity 3n plus 1 over n cubed minus 4. So we're going to go ahead and find out a bn, which is a simpler series, 3n over n to the 3rd, which turns out to be 3 over n squared. So bn is going to equal summation n is equal to 1 to infinity 3 over n squared. Okay, so limit comparison test, limit n goes to infinity. This is my an over bn. Limit n goes to infinity, an is 3n plus 1 over n cubed minus 4 divided with 3 over n squared. Limit n goes to infinity. You could just call it 1 over n squared. That would work out just fine. It doesn't have to be 3 over n squared. 3n plus 1 over n to the 3rd minus 4 times n squared over 3. Okay, limit n goes to infinity. That's going to be 3n to the 3rd plus n squared over 3n to the 3rd minus 12. Now, same degree in the numerator and denominator. The limit is going to be leading coefficient over leading coefficient, which is 3 over 3, and that's going to equal 1. So we can say, using limit comparison test, using limit comparison test. Using limit comparison test, the series we were looking at, 3n plus 1 over n to the third minus 4, n is equal to 1 to infinity. This series also, oh, what did we know about the bn? What did we know about the bn? Did the bn converge or diverge? 3 over n square, this is a convergent p series. This is a convergent p series. Convergent p series. So that means this series also converges. This series also converges. That's all. In this video we talked about the direct comparison test and the limit comparison test. So when you're doing limit comparison test, you want to compare your limit, compare your find the limit, find a bn where bn is simpler, and if the limit of an over bn as n goes to infinity turns out to be a finite, non-zero finite number, then both series converge or they both diverge. And when you're trying to do comparison test, direct comparison test, in that case you want to find either a bigger series, you either want to find out a bigger series that's convergent, or you want to find out a smaller series that divergent. If you find a bigger series that diverges, that's of no good to you, because you cannot say anything about the smaller series if you find a bigger series that diverges. That's all for this video. In the next video we'll talk about ratio and root test for series convergence.